This is the second lecture on interrupts for Comp 375 Computer Architecture and Organization at North Carolina A&T State University. Interrupts are the means that the operating system can get control whenever something happens, either external or internal. The operating system often needs to respond immediately when an external event occurs. Think about your mouse. When you move the mouse, it moves on the screen. As you move the mouse, it generates an interrupt. The operating system gets control and repositions the mouse icon on the screen. It has to respond immediately, so the mouse will always be in the position that the user wants. When an interrupt occurs, the hardware has to save the current state of the running program so that it can come back to that program as if nothing had happened. The first thing a hardware does is saves the current program counter and the status flags, and then loads a new program counter and the status flags. Because the program counter always contains the address of the next instruction to be executed, the execution starts at a new location. This is typically in the service routine of the operating system. First thing it will do is save the registers, and then looking at the hardware status, try to determine what was the cause of the interrupt. After determining what is needed to be done, it will do what has to be done. When it's completed, it will restore the registers that it had saved earlier, and then execute an interrupt return instruction, which reloads the saved program counter and status flags. There are three general categories of interrupts: external interrupts caused by outside devices, internal interrupts caused by programs, and then program-generated interrupts, which are intentional efforts to call the operating system. When an I/O device completes its operation, it will inform the operating system by an external interrupt. If the device gets an error, something doesn't work correctly, it will also interrupt the CPU so that the operating system can try to recover from the error. There's also a timer interrupt, which interrupts at a regular basis so the operating system can get control. This helps makes the CPU scheduler work effectively. Internal interrupts are often called exceptions because they're often errors, although not always. Some errors are detected by the hardware, such as division by zero, or if you have a bad pointer that causes you to address memory outside of your program area. These are detected by the hardware and it causes an internal interrupt. A page fault is not really an error, but it means that the program has executed an instruction or reference data that is not currently loaded in RAM. The page fault occurs and the operating system gets control, figures out what to do about finding more memory for this program, updates the page table, and then restarts the user's program at that instruction. Programs can also intentionally create an interrupt with the interrupt instruction. In the Intel machine, it's INT for interrupt. This is basically a function call to the operating system, asking it to do something. Most architectures have privileged instructions. That is, there are some things the operating system can do that user programs are not allowed to do. In particular, privileged instructions, for instance, for I/O. There's a start I/O instruction that only the operating system can do and not user programs. Memory management, changing your page tables, and of course, enabling or disabling interrupts. User programs cannot do that, but if that needs to be done, they can make a request to the operating system. There are 4 different privilege levels in the Intel CPU. Privilege level 0 is for the operating system kernel, runs at the highest privilege level. User programs run at privilege level 3. And other parts of the operating system and tasks run at different privilege levels depending on how important or how quickly they have to respond. You're doing a virtual click at this time.
Thought you could forget the powers of two, eh?
You need to know them because they show up in many places. This is the Intel flag register. You will notice that there are 2 bits representing the privilege level. It's called the I/O privilege level, although it impacts more than just I/O. There are, of course, 2 bits for it. There's also the interrupt enable flag that is set to enable interrupts or to turn off interrupts. As we mentioned, when the interrupt occurs, the hardware saves the registers and loads and saves the flags and those new flags. The new flags will have the privilege level set to operating system mode and will disable the interrupts. Of course, users run at the lowest privilege level and interrupts are enabled for user programs. So as we change the flags, that puts the program into operating system mode and disables the interrupts. Here's microcode how it might possibly be able to implement an interrupt. We've added 2 new registers on the far right side. These are read-only registers that contain data about the interrupt system. So if the microcode detects that an interrupt is happening, then it would first copy the interrupt save address to the memory address register. This is the address in memory where the current user's program counter will be saved. It will then copy the program counter to the memory buffer register and write the user's program counter out to memory at the specified address. It will then copy the interrupt new program counter value in the far right register into the program counter. This will mean that the next instruction the machine executes will be in the interrupt service routine of the operating system.
Thought you could forget microcode.
Microcode implements the instructions and other parts of the CPU. There are several different aspects of interrupt design that have to be considered. One question is, when will the hardware or the microcode recognize the interrupt? Usually a status line is set to indicate an interrupt has occurred. Most machines will handle the interrupt after the currently executing instruction has completed. It tries not to stop in the middle of an instruction, although some internal interrupts or exceptions may occur in the middle of an instruction. Where's the program counter and the flag saved? Well, that depends on machines. Some save them in a fixed spot, some on a stack. What do we save? How do we find the entry point? And how do we get this machine running again? Most machines have an interrupt vector. The Intel Pentium i5s, i7s, all of them have a low address array that contains the addresses of the routines to handle certain interrupts. So when an interrupt occurs, the hardware provides the operating system with a index, and it uses that index into the table of the interrupt service routines to determine where it's going to go to the part of the program to handle that particular device. Now, there's a question of whether you want to return to the currently executing instruction after an interrupt or to the next instruction. Sometimes you can't go back at all. For certain internal interrupts, say you've had an addressing error, there's just no reason to keep going with the program. You don't want to go to the next instruction. That would ignore the error. So typically, the operating system gets control, prints a nasty message on your screen, and stops your program. For other interrupts, such as page faults, you want to re-execute the instruction. That is, the one that got the error because it was accessing memory not currently located in RAM. Well, try that same instruction again. For other interrupts, the system may decide to more or less ignore them. For instance, integer overflow. If that causes an interrupt, the program may decide, doesn't matter, just keep on going. Execute the next instruction. Interrupts occur all the time. I did a simple measurement and found out that about 4,000 interrupts per second are occurring while I'm just sitting here working on my PowerPoint and other things on my machine. So it's very possible that while the operating system is servicing one interrupt, another interrupt may occur. How do we handle two interrupts at once? If you store the return address of an interrupt at a fixed location, the second interrupt will overwrite the first interrupt's return location. That doesn't work real well. Some machines will use a stack, a special operating system stack, to store the return address of the interrupts. Another way to do it is to disable interrupts. Most interrupt service routines start with interrupts disabled. That means that if an interrupt occurs, it will be queued or it will wait until the interrupts are then turned back on. This prevents interrupt service routines from being interrupted while they're processing. It is generally possible to disable interrupts or to keep them from occurring until the interrupts are turned back on. The Intel processor has an interrupt enable flag, and if it's turned off, then interrupts will not occur until the interrupts are once again turned back on. You can generally disable external interrupts, but not internal interrupts. You don't want to disable interrupts for a long period of time because they may cause missed events. Here's our internal EFLAGS. You can see once again there's an interrupt enable flag. Many devices will interrupt every time something happens. For instance, every time you move the mouse, one small unit. By the way, the smallest unit of a mouse movement is called a Mickey. And if you move the mouse, then it will cause an interrupt. You need to capture every interrupt to make sure you know where the mouse is. Also, of course, with all the other devices, every time data comes in from the network, something comes in from the disk, you want to make sure that you process it. Sometimes if you don't process it right away, another event will occur and will overwrite the information from the first event, and therefore you may lose some information. Most systems prioritize interrupts because some devices run much faster than others. If two interrupts occur at the same time, the one with the highest priority should be serviced first, which is typically the most important device or the fastest device. Here's a table of relative device speeds. You can see if we have gigabit Ethernet, then data rates of 1 billion bits per second. Graphics displays, I think, are probably even faster than that, although this shows them slower. And hard disks and other things are slower. Way down at the bottom, you have keyboard and mice. How fast can you type?
How come they got computer mice but no computer rats?
You're just not cute. Now bunnies are.